All right, kids. So here we go. The last one: Bronsted-Lowry bases and acids and titration. So Bronsted-Lowry, unlike Arrhenius, who said acids produce H plus and bases produce OH minus when they're in water, Bronsted-Lowry came up with that a acid is a proton donor. So anything that would give up an H plus could be an acid, and anything that would receive that H plus, that proton, would be a base. So here you see the ammonia picking up the H plus to become NH4 plus. So it picked up the proton, so it's a base. Here you see H3O plus losing that proton to become H2O. So that is losing a proton, so that is an acid. And when you put it all together, you get water plus ammonia. The water molecule has the acidic proton going to the base, and that becomes NH4 plus, and the base is OH minus. All right, so conjugate pairs, if we have an acid here, which is the water, because it lost a proton, it becomes what we call a conjugate base. And when we have a base, which here is the NH3, when it picks up the proton, it becomes a conjugate acid. And we talked about how when we played Heads Up 7-Up in class, I gave a bunch of people a sticker and told them they were acids, and that sticker represented a proton or an H plus, and they had to go stick it to someone in the class. And when they did, that someone was a base, and when they stood up, the base now had the sticker, so they were the acid, right? They had the H plus that they could give back. It was their turn next, and the ones without the sticker were now bases because they had given up their sticker, so the acid had given up its proton to become a base. And hopefully that made some sense to you. So here are some examples. H2SO4 becoming HSO4 minus and water. So H2SO4 is losing that proton. So this would be the acid. Ooh, look at that. And then therefore this one on the left side, the other reactant, has to be the base because that's the one that picked up the proton. And that's what we see here. So OH minus went to water, and by doing that, now it has a proton to give up, so that becomes the conjugate acid. And the acid, or the what's left of the acid, so H2SO4 become HSO4 minus, so now that is the conjugate base because it can pick up a proton going the other way to go back to H2SO4. So that is the conjugate base. All right, so HSO4 minus, that should be a minus, plus water. This now has a leading proton still. This has the leading proton, but the one that loses it is the HSO4 minus to become SO4 2 minus. So since this lost the leading proton, that is the acid, and water picked up that proton. That is the base, and then the base becomes now a conjugate acid. So the water is now a conjugate acid, H3O plus, and SO4 2 minus. HSO4 minus, when it lost that proton, is now the conjugate base. If you can read that chicken scratch, there we go. Conjugate base. So ammonia and water. Ammonia is picking up a proton from water to become NH4 plus. So this therefore is the base. Ammonia is the base. So it's not always the one listed first. It's the one that picks up the proton. H2O became OH minus. So it lost a proton. So H2O in this case is acting as an acid. Now, as you can see, sometimes water is the acid and sometimes it's the base. And then NH4 plus now has the proton. It has the sticker. So that is the conjugate acid. And OH minus lost its proton. So that is therefore the conjugate base. So that's what we discussed in class. And we did Heads Up 7-Up. And now we will talk about titration. So we did one of these in class even, where you try to reach an endpoint. You try to make the acid or base, you add base to an acid or you add acid to a base so that they are equal points. And that allows you to figure out whether one's molarity is an unknown molarity, basically, if one of them is unknown. So a reaction between an acid and base to the point of neutralization, so the point where they make water, is called an endpoint. This is when moles of acid equals moles of base. And usually the endpoint is determined by a pH meter or an acid-base indicator. So in lab, we use phenolphthalein, and some of you may have used the universal indicator. So it's the amount of protons, and this kind of means concentration, which I didn't mean to do, but it means the amount of H plus equals the amount of OH minus, and that's what the endpoint is. So when the moles of H plus equals the moles of OH minus, that is an endpoint. The equation we follow, Na is equivalence. So the equivalence of acid times the molarity of the acid times the volume of the acid equals the equivalence of base times the molarity of the base times the volume of the base. So what we did in class was we played a little Space Invaders to help you see this. And the way we did that was we saw these as acids. So these are all the H pluses. And every time I add OH minus, I'm going to make water. So when I make water, I get rid of that acid. But as you can see, the pH of the solution is still acidic. There's still a whole lot of H pluses. So it'll take me a while of shooting out all these H pluses with base to make them turn into water. I'm going to get rid of that so it stops making noise. So that gives you this sort of a graph when you graph it. And down here, there's nothing but acid. So down here, we have acid because even though the base is being added, we have more and more acid still available in the beaker. So the pH is acidic. So the pH here is going to be, let's say, a 2. Let's say a 2. Let's say, oh my gosh. All right, that's 2. The equivalence point is where the acid equals the base, and that would be 7. So up here, the pH is 7 because the acid is equal to base, and we've hit all those Space Invaders of H pluses with our base as we're adding base. So now the next drop of base we add is going to raise the pH to a basic pH. Next drop after that, it's going to raise it even more, and we're going to get up here to a highly basic pH of like 10 up here because we're adding base and there's no acid there anymore to pick it up. So some examples of this are right here. Let's do this and we'll all right, so we have HCl and NaOH. So the molarity, the equivalence of acid. So HCl has one leading hydrogen. So its equivalence is 1. There's 1 proton per mole of HCl. The molarity of the acid is what we're looking for. It says, what is the molarity? So that's right there. And the volume of the acid that we used is 25 mils. So that's 25 mils. And then we have the NB. So the NB is for NaOH. Every mole of NaOH has 1 OH, so the NB is 1. The molarity of the base is 2.0 molar. NaOH is 2.0 molar. And the volume of the base is 15 mils. So that's how we get that. Now we plug all that into the equation NaMaVa. So 1 times question mark times 25 equals 1 times 2 times 15. So we get whatever the MA is times 25 equals 30. And so when we divide both sides by 25, we get MA equals 1.2 molar. So the other example for this was we have NaOH and we're neutralizing it with acetic acid. So the base NaOH has 1 OH per mole. There's 1 OH per mole. So the NB is 1. The volume we used is 15 mils. So 15 mils is the volume, and we're trying to figure out what the molarity is. The Na, the acid we're using, and this one's a little confusing, but it's acetic acid, but that acetic acid only has 1 leading proton. These hydrogens are in the anion and not part of this acidic proton here. So there's only 1 leading proton, so the Na equals 1. The molarity of the acid is given as 0.02. So that's why that's there. And the volume of the acid is 7.5 mils. So when we put that into that equation, we get 1 times 15 times question mark equals 1 times 0.02 times 7.5. And when you solve for that, you get the molarity of the base is 0.01 molar. And that is acids and bases, kids. So hopefully you will now be ready for your big exam. And please email me if you have any questions.